Okay, so I'm talking right now about section 3.1, which is quadratics, and these are the application problems that we didn't get to in class. So I'm going to start with number 80. It's a landscaping problem. We're given that a rectangular garden plot is going to be enclosed with a fence on 3 of its sides because there's a brick wall on the 4th side. So I drew a picture there of a rectangle, and there's a wall on one side, so we only have to worry about 3 sides. So we have 100 feet of fencing material. So that's kind of the key thing that we need to start with here. And so I'm going to put P for perimeter. The perimeter is going to be 100 feet. Okay, so perimeter, we have to figure out what we're going to do with that. What variables are we going to use? So we have to make them up in word problems. And that's one thing that I think a lot of people have a hard time with, is just making up variables. So we've got width and we've got length. I generally think of width as the shorter side, so I'm going to make that W. And of course then the other side is also W, and then the long side is going to be L. All right, so that means that the perimeter is going to be W plus L plus W. So we have 2 W's and we have 1 L. So that's the perimeter. All right, so the other when you have something like this, you have 2 unknowns. You need to have at least 2 equations. So the other equation is the area. So we're trying to find the dimensions that are going to yield a maximum area. So we need to find an area problem, and then it needs to have only one variable. So I'm going to rearrange this to solve for L. So this all equals 100. Course. So I'm going to rewrite the 100 over here without the feet. And I'm going to subtract both sides from, subtract 2W from both sides. So I get minus 2W and minus 2W. And that means I have L, the length, in terms of W. So that gives us 100 minus 2W. All right, so now we know the length in terms of W. I'm just going to rewrite it right here, 100 minus 2W. So now all 3 sides are in terms of W. So now the area is always the same formula. You've known that since elementary school, length times width. And so now we know that length is 100 minus 2W, so that means we just can replace the L with 100 minus 2W. And then the W is still there. And we end up with, we're going to distribute that W, 100 W minus 2W squared. So this might not look really familiar to you, but it is a quadratic equation. So I'm just going to rearrange this right here to be negative 2W squared plus 100W, and then if it was in the form of a quadratic, it would be plus 0, because that would be our C value. So now hopefully it looks a little bit more like a quadratic to you, and you can now take this and kind of figure out what it's going to look like. So the first thing you got to think about is which way is this going to face. So because of the negative right here, we are going to have a quadratic that faces downward like this. And that means we're going to have a maximum. That maximum right there is the maximum area that we're looking for in the problem right up here. So this maximum area right here, that is the maximum. Okay, so we just created a quadratic with the given information, and the vertex is the maximum that we're looking for. So now we just need to figure out what that point is to tell us what the maximum width or length is going to be. Now, if you've got to stop and think about what is this graph? Like, what are the 2 different dimensions of this graph, the axes? So we've got the quadratic that we're working with here equals area. So the independent variable is W, that's width, right down here. So the width of the fence and the width of the rectangle. And then on the left over here is area. So length doesn't actually come into play here. It's just the width. And once we find the width, then we can plug that back in to find the length, and we'll have all of the information that we need. So That means that h in the hk, so this is hk, right? hk, which in this case is width. That's the h, the x value right here, because this is normally x and this is normally y, right? So the x value is width and the k value is area. All right, so the number we're going to get here is width area, the maximum area, and what the width would be at that maximum area. Okay, so stop and think about that if you need to pause the video and look back through what I just did. Make sure it makes sense. All right, so in the HK equation, our vertex equation, we know that h in the HK is, in this case, the width w. Okay, I'll write it out so because I know all these different variables start to get confusing. Is going to be negative b over 2a. Well, what's b and what's a? In that case, we've got to go back and look at our quadratic. So this is a, this is b, and this is c. Okay, so we're going to use those for a, b, and c. So we get negative, and then b is 100 on top. And on the bottom, we get 2 times a, which is negative 2. All right, so if you work that out, the negative and the negative cancel out. You get 100 over 4, which is 25. And it's in feet, so it's going to be 25 feet. So now we know the maximum width to maximize the area of this area that's going to be fenced with 100 feet of fencing. So now we know the height, the width. We know h, the width. And we need to find the length. So we're going to use this formula that we have up above, this one right here. We're going to just use it and plug right back into it. We've got 100 minus 2 times w, which is 100 minus 2 times 25. So 100 minus 2 times 25 is 50. Okay, so we have the width here is 25, this one is 25, and this one is 50. Make sure it makes sense. Stop, go back to your picture, look at what you've written down, and make sure it all makes sense. Does that add up to 100 feet of fencing? 25 plus 50 plus 25 is 100, so it looks like we did it right. I also want to show you, the graph of this. So I changed the, and this is an opportunity to show you changing the axes. So if you click on this little wrench up here, you get this, and I changed the x-axis to go from, and I played with it a bit till I got it to look like what I wanted, but I went from negative 20 up to 60 so I could kind of zoom in on the graph, and I made the y-axis, which is the area, go up over 1200. I made it go up to 1300. And go down below the x-axis a little bit so I could see what was going on. So it crosses right through 0 here, 0, 0, and it crosses again at 50. So really what you get are two answers. You get 0 and 50 as your roots to this. But what we're looking for in this is the maximum right up here, which is 25 feet and 1250 square feet, which is the area. Okay? So a lot of information there, but hopefully that helped you to understand how to do one problem. We're going to look at some more here. Okay, so the next problem we have here is number 83. It's a physics problem, and it has to do with a thrown ball and the height of it with respect to time. This is a very common kind of problem because anything that moves through the air usually moves in the shape of a parabola because of gravity. So in this situation, it says the height of a ball that's thrown directly upward from a point 200 feet above the ground. So basically, somebody must be, standing on top of a building or something, and they throw this ball, and then it goes down. So you end up with that shape, basically. And we're given the formula. So we don't need to worry about the 200 feet. We don't need to worry about the 40 feet per second. But you can kind of see in the formula that they figured out already where the 40 and the 200 come into play. The 16 actually has to do with gravity, the force of gravity and the acceleration due to gravity. So here we've got h of t, the height with respect to time, basically is why they're using h, is negative 16 t squared plus 40 t xt plus 200. Okay, so t is the amount of time elapsed since the ball was thrown. So they want us to sketch a graph. Well, I just did. So that's the general idea of the graph here. So time 0 is right when it's thrown, but it's 200 feet above the ground. So if we do this, we end up with a graph that basically looks like that. So this is time 0. So here's 0. So now we've got t and h. So which one is going to be the x-axis and which is going to be the y-axis? You kind of have to think about that one for a second because it's not given. So t is the independent variable. Also, just think about time is not changeable. Everything depends on time. So time is always going to be the x-axis. Okay, time does not depend on anything else. So this right here is 200. We start right at 200 feet, and then it goes up and then back down. So that's the graph of h. It's facing downward, and we know that, well, partly because of the shape that I drew, but also because there's a negative in front of the 16. So they want to know, when will the ball reach the maximum height, and what is the maximum height? In other words, what is the vertex? And we know how to find the vertex. It's fairly simple. So if we know A is negative 16, B is 40, and C is 200. So HK is what we're talking about here, is what we're trying to find. And in this case, HK, H is the x-axis, so that's T. And now it gets confusing because the other one is height. So I'm going to do this. I'm going to say HT, or yeah, for height. Okay. You can also say like T and then put the whole word height if you'd like. All right, so HK, the vertex is, so T in the vertex is negative B over 2A. And that is going to be negative, and you put 40 on top, and 2 times negative 16 on the bottom. So what we get here, the negatives are going to cancel out. We're going to get 40 over 32. Which is 5/4. And you can also write 1.25 because that makes a little bit more sense because we're talking about seconds. So this happens right here at 1.25 seconds. Okay, so that's our x coordinate. So there's a few ways to find the y coordinate at this point. You could just plug 1.25 back into the equation to find what h is. What the height is at that point. The other thing that you can do is you can do the formula for k. So k is going to equal the height. That's the vertex coordinate k. And that is c minus b squared over 4a. So we're going to have c, which is 200, minus b squared, which is 40 squared, over 4 times negative 16. And if you plug that into your calculator, you just find that the height at that point is going to be 225 feet. Okay, and feet, we know it's feet because if we go up here and look in the problem, we have feet as the as all of the units here, so we know it's feet. Okay, so we end up with 1.25 seconds and 225 feet as the vertex. So that is that answers the question, when will the ball reach its maximum height? Well, at 1.25 seconds. And what will be its height? It will be 225 feet. All right, we're going to try another one. Okay, I decided to do this one because it was a little confusing and I wanted to show you how to think through this one. So this is a construction problem. It's about a farmer and his fencing. So a farmer has 400 feet of fencing available and he wants to make a corral that looks like that, and he wants to maximize the area inside it with the 400 feet of fencing. So what should the dimensions be to maximize the area? So the first thing you need to do is figure out how the heck we're going to do this. The angle is a little bit weird the way we're looking at it from above, so I just wanted to show you that each piece of fencing basically looks like this. Oh, That was not lovely. So each one of them looks like it's got 3 bars going across. So that is one piece of fencing. When I first looked at this, I thought that each individual piece was a piece of fencing, which made it very confusing. But this is like a piece of livestock panel, basically, if you know what that means. Okay, so how many sections of X do we have and how many sections of Y do we have? Well, we've got X here, and we've got X over here and over here. So we've got 4 panels of the size X. And then Y, we've got this one, and then we've got Y here, and we've got Y here. Okay, so we've got 3 of them. So we've got 3 sections that are panel Y. And they have to, together, all add up to the perimeter of 400 feet of fencing. And the perimeter is a little weird because there's also a piece in the middle. But anyway, that's the length of all of the fencing. All right, so now the area is we want to maximize. And you can do both corrals and it still works out the same. Strangely, I did it both ways and it works out the same. So we're just going to look at one square because if we maximize one, we've maximized both, basically. So, if area equals X times Y, so that's the area of one of the corrals. So we're maximizing the area and we want to find the dimensions of each corral. So now we need to use these 2 formulas to figure out how to move forward with this and come up with a quadratic equation. So I'm going to do one more step here for you, and then I'm going to have you try this for the check it out. I'm sorry, for the Ed puzzle. So there's a couple different ways you can do it, and I think I'll just tell you what I did was I solved the top one for Y. So you've got 4x plus 3y equals 400. So why don't you start with that, solve for Y, and then you will take that Y and plug it in right here to come up with a quadratic, and then you're going to create a graph and find the maximum area. Okay, so what I want you to tell me is what is X and what is Y. So tell me the dimensions of each of the corrals, and just tell me X and tell me Y in your answer. Okay, good. So here's how you're going to work this problem. First, you need to rearrange to solve for Y, and I put it in, I switched the order of the 2 parts of it to make it look like Y equals mx plus b. Now we need to take this Y and put it in for, we need to put it in for the Y in the area formula right here, so that now we can maximize the area, because that's what we're looking to do. So I put it in red here, negative 4/3 x plus 400/3. And if you notice, if it's in Y equals mx plus b form, then when you multiply it times x, it ends up in the quadratic form. So that's a nice bonus. So then you can figure out what a and b and c are. There is no c, so it equals 0. So now we're going to find the h value of the vertex, because what we end up with here is, if you look at this quadratic here, we end up with, again, and that you should have given it away when it said a maximum area, so you know it's going to face downward. So we're looking for h in the hk, because when you graph this, again, we have area over here, and down here on the bottom we have x, because that's what we have as the independent variable in the area equation. So h, this value right here, is x. And the k value in this case is area, which we don't care about. So I should not have put k right there, because it's not k. So what we're going to do right here is we're going to find h, which is the x value, by using the vertex negative b over 2a. And we find that to be 50 feet. So right here, the x value is 50 feet. Okay, but we don't care about the k value. They didn't ask us about the area. If they'd asked, we could answer it with this. But what we wanted to know here is, what is y? So you have to take the 50 and put it back into one of these equations here. So I did that here. Okay, I plugged it back in. and I found it to be 200 thirds feet. So y is 200 thirds feet. So now we know the dimensions of this corral, and we know each x value and each y value. The x's are 50 feet, and the y values are 200 thirds. So I graphed this as well, so you could just see it. It crosses at 0 and 100. Those are the roots. And you end up with the maximum of 50 feet for x. All right, so hopefully you were able to do part of that. And that's the end of this part of the lecture. There are plenty of things to use this for, but I think 3 is probably enough for now.